All right, we're at 22.4 dispersion and prisms. I'm also going to include 22.5 on the rainbow because it really is related to dispersion. Um, we're looking here. If you recall, 589, you can see 600, 589 would be right here. I said it was orange. You can see there that indeed 589 nanometers. This is nanometers at the base here, and this is the index of refraction. And you can see that the index of refraction, not only does it depend on the material, we have crown glass, acrylic, and fused quartz here. Not only does it depend on the material, it also depends on the frequency. You can see how the index of refraction for like this lavender, this purple, is 1.53 in this crown glass, and it's only 1.51 for red. So it's not only material dependent, it's frequency dependent. So if you were making a lens, you would want to use fused quartz because you see here the spread is almost 0.02, whereas here it's closer to 0.01. The spread and the index refraction. That's a discussion of dispersion, and we use this. You can see a prism. A prism incident light comes in, and it's bent by the index of refraction. Then it's bent again as it exits, and depending on the color, it'll spread the colors. Yes, why you get a color spread in a prism. Because n varies with wavelength, the prism disperses the white light into its various spectral components. So you have white light coming in through these slits. You go through the prism, and it spreads them out. This is about 400 nanometers. This is about 700 nanometers. So it's increasing wavelength over here. The different colors of light that pass through a prism are refracted at different angles because the index of refraction of the glass depends on wavelength. Violet bends the most, red light the least. We use that in things like a spectrometer. Here, this is a diagram of a prism spectroscope. The colors of the spectrum are viewed through a telescope, and the prism spectrometer within. They're showing you a prism spectrometer with different components. So this is a prism spectrometer. They use spectrometry they look at different stars to see what some of the component gases are. So it's used in astronomy. It's used in it's used in a lot of different technologies in chemistry. Here's an example here of this is a helium spectrum. If you were to look at sodium, it emits only 2 wavelengths. So here, this is a image of helium. This spectrum of helium. So spectral analysis is used in the measurement of wavelengths emitted and absorbed by substances, and it's used in many areas. It's to identify molecules. It's astronomers use visible light spectroscopy to identify the elements on distant stars. Geologists use spectral analysis to identify materials. And we're going to continue on, even though this is section 22.5. I'm going to continue on with the rainbow because it's still about dispersion. And I've got a little. Oh, I can't do that. I have to change share, new share. Oh, where is my, here it is, Mathematica. And I've got a little demo. Now, if I were to keep it, well, let me just put in here 1.333, which is the index of water. You can see there's not much spread. This would be the beam, and you can see there's not that much spread. So I'm going to increase the index of refraction, 12.4. That's a big index of refraction, but it's only for the teaching purposes. You can see how, as it comes in, the index of refraction of the water is disperses the colors. It bounces off the backside, and as it comes, the index of refraction from the water to the air, causes this to disperse even more. So this is what's going on in a rainbow. Now, if you're standing here, you're intercepting. Like if you're standing here, you might see the red from this droplet. Well, for another droplet that's further below, you might see the green, and another droplet that's further below, you might see the purple. So you're seeing the colors from individual droplets, and it makes this beautiful image, composite image of all the colors of the rainbow. So what you see is actually taking place on the inside of your eye. There's nothing really out there than water droplets that you can't reach out and touch a rainbow because it's all happening on the inside of your eye. Let's go back to the PowerPoint, and let's see, there it is. So here is, you can see the red is at the bottom, the violet is at the top. You're seeing droplets from, white light is coming from this droplet down here. You're seeing violet. The droplets up here, you're going to see you're going to see the red. And occasionally you get this double rainbow, because you'll get it, the light will reflect off the inside of the droplet back and then back out, so you get this double rainbow. But you can see that it's much it's faded. It's neat when you see them. Okay, and I'm going to skip Huygens principle. I don't think it really enhances our understanding of either reflection or refraction. You're welcome to study it. I don't think it's an MCAT topic, but I'm going to skip straight to the other than I will discuss this image, and they're showing a barrel rolling on concrete, and then how it rolls on grass. They're giving you an image to think about. I like what I learned when I was in studying physics of a marching band, and then not a marching band, soldiers marching on concrete at an angle. And if they were to suddenly march on concrete and you start marching in mud, then you'd get this turning, and the ones marching in mud would be slower, and so you'd get these stripes of soldiers, but the ranks would close up and shorten, get shorter here. The spacing between the soldiers would get shorter, and that's analogous to what's happening in the wavelengths of with indices of refraction greater than 1. Okay, I'll stop it here, and then we're going to go on to total internal reflection on the next one.